This recording is to introduce and discuss sampling distributions in the quantitative world, the world of μ's and x-bars, things that we measure. At any time during the video, you can ask the substitute to please pause the video for you. I will do so during certain times. Please keep in mind that I have asked the substitute to be walking around and keeping you on task, which means not using your phones or your iPads. The better you can pay attention to today and tomorrow, then the easier this chapter will be for us, and it's a very important basis for the rest of inference. So first thing I'm going to do is show you the answers to this little quiz. Hopefully you only did one column because the other two are identical to it. Those are for you to practice. So here are the answers. I will pause briefly. All right, you can always go online to look at the notes if you didn't get this finished. Okay, next page is taking a look at the objectives for this chapter. And the objectives are on the back side of that page I gave you last week. We have covered the first 8 objectives, although I will be taking a look back at 7.2 when I return. Today and the rest of this week, we will be doing the last 3 objectives, finding the mean and standard deviation of the sampling distribution of sample means of x bars, checking the 10% condition before calculating sigma sub x bar, explaining how the shape of the sampling distribution of x bar is affected by the shape of the population distribution and the sample size, and if appropriate, using the normal distribution to calculate probabilities involving x bar. So the first thing we're going to do is review our notation, and this AP exam tip says notation really does matter, and if you don't know it, don't use it on the AP exam. But we're just learning it right now, so try to learn it appropriately. You had a team quiz last week where you had to figure out if you knew this, and you will have an individual quiz, which we will see if you know this or not soon. So let's flip over the empirical roll quiz, and we have this little chart. This is in the Rho P hat world of last week. Let's see what you can fill out here. Okay. I hope you don't think this was a bit of a trick, but we don't actually have a symbol for the population's standard deviation. In fact, that's one way that you know you're not in this world, is because they don't give you a population standard deviation. We know that rho equals mu sub p hat because we have unbiased estimators and simple random sampling. If the 10% condition passes, then I've made the formula a little bit bigger down here. We know that we can find sigma sub p hat by doing the square root of rho times 1 minus rho divided by n and taking the square root of that. All right, so let's go to the world we're going to be studying this week. And this is the x bar mu world, so see if you can fill out the chart below. Okay. Here are the answers for the mu sub x bar world. Again, we know that mu equals mu sub x bar if we have unbiased estimators, and that helps with the simple random sample. If we check the 10% condition for spread, we have a new formula. This is different than in the other world. It's actually a bit easier. Sigma sub x bar instead of sigma sub p hat is now the population's standard deviation just sigma divided by the square root of n. And that again is if the 10% condition holds. And then we again have population size and sample size with a capital N and lowercase n. To practice your symbols, the bottom of this worksheet, you can fill in those and the answers will be posted online, but please don't do it right now. You can do that for homework if you're having trouble or need some practice. And there will be a quiz sometime this week on those. All right, so for sample means, there's our 3 objectives. We have 3 conditions we have to check. That is center, and we have unbiased estimators, and we have spread, and we have shape. So again, we did this last week. where we had the populations distribution. And you don't have to find this just to remember what we did. This is the population distribution. It has a mu, and I believe that mu was about at 68 inches. Might have been 68.5. And it has a sigma, which I don't remember what it was, but it also has a range, and I remember that that was 16.5 inches. And then we each took a sample of size 4. We plotted that distribution. So this is sample data. This is one sample's distribution. This is my individual little x bar and my individual range. And then we all put our individual x bars onto this distribution, which was the sampling distribution. We also put our range values down here on the range distribution. And the interesting thing about these two sampling distributions is that for the mean of our sampling distribution, which is mu sub x bar, approximately 68.5, is very close to being equal to, and I think, yes, the population's mean was 68.49. So if I go back here, 68.49. That's called an unbiased estimator. And so we did have random sampling, but the fact that the population balances right, or the sampling distribution balances right where the population does, is what makes it an unbiased estimator. And if you notice down below here at the range, the actual population's range was 16.5. Our range is more like about 8. This is a biased estimator. Even though we did simple random sampling, that wasn't enough to make sure that we would have an unbiased estimator for range, and that's something we'll talk about. But so it's not just simple random sampling that gets us there. We see that sampling distribution means are a good estimate of the population mean, but sampling distribution ranges do not estimate the population range very well. So that's something we just have to keep in mind, and we'll discuss a little bit later on. All right, so moving right along, we have the center check and mu sub x bar. Master x bar will equal the population mean if we have random sampling. We've seen that sample standard deviation mean is an unbiased estimator of the population mean. Then we have the 10% condition. This is the spread check, and that is also the same as in the other world. If our sample is less than or equal to 1/10 of our population, then we know we can find the standard deviation of the sampling distribution by taking the standard deviation of the population and dividing it by the square root of n. And that's what this page is telling us. This page right here is also telling us that for the shape distribution, if the population distribution is approximately normal, then the sampling distribution is also approximately normal. So a normal population produces a normal sampling distribution, and that is always going to happen, and there's nothing we have to do to check. Just look at the prompt to see if it tells us about that. So this is the page that proves that we do have that mu x bar is going to equal mu, and that sigma x bar is going to equal sigma divided by the square root of n, and I will discuss that when I get back. But now we're going to hand out the next worksheet if we could, and talk about pregnancies and women. It looks like this, and I'll pause while we get that handed out. Okay, so let's start this problem. It says the length of human pregnancies from conception to birth vary according to a distribution that is approximately normal. So that tells us that the population is approximately normal. It has a mean of 266 days and a standard deviation of 16 days. So what I've been given so far is my population is approximately normal. The mean of the population is 266 days. and the standard deviation of the population is 16 days. So that's my given information. Now it asks me to find the probability that A, randomly chosen pregnant woman, has a pregnancy that lasts for more than 720 days. All right, so first off, A means 1, and I will tell you that these 3 checks that we need to do for center, shape, spread, usually do spread next, center, spread, and shape are all going to be met, and I'll just go through that very quickly. We know that mu sub x bar is going to equal mu because we did this with a simple random sample of size 1. The spread is going to meet the 10% condition because 1 is certainly less than all the pregnant women out there. So I can find sigma sub x bar by taking 16, which is the standard deviation of the population, divided by the square root of 1, and that leaves me with 16 still. And the shape is going to be approximately normal because that was what the population was. So now I can do this problem. And what I would like you to do is always put a capital N 266, 16. That comes right from the given information, and that is always going to help you know what to put in the middle and how to find the standard deviation. So let's put our z-scale down first. That's our z-scale, and now let's put our, I guess it would be kind of an x-bar scale out there. And it starts at 266, and it goes out by 16s. So we can access our calculator and do norm dist. In norm dist, we put in the 266 and the 16, and that gives us these numbers, which I will bring out to my workplace or space. And now I can fill those in: 218, 234, 250, 266, 282, 298, and 314. There we go. Pi again, isn't that fun? All right, you can ask the substitute to pause the recording anytime you want to, but I'm going to go ahead with trying to find that a randomly selected pregnancy, so this is just an X, it's not an X bar because we didn't take a mean, we just took 1, is greater than 270. That's approximately equal to a z-score being greater than something. And if I put this on the curve, 270 is going to be about right here. Remember to shade it all in and put 270. 270 equals an X right here. So I know my z-score is going to be a positive 0 point something. And how do we find z-score? We take your score, which is 270, minus the mean of 266, divided by the standard deviation of 16. So we get 4 divided by 16, which is 0.25. And we know our answer has to be a bit bigger than 16%, hence the reason we did the empirical roll quiz this morning. And you can look that up on your table, like I will do right here. Positive 0.2 over to 5 gives me a 0.5987. So according to our textbook, this right here is not the 0.5987, it's down this way. So 270 really should be a little bit more shaded like that. And I can put my curve up here and do a little bit more shading. So my answer is not 5987. My answer is going to be 1 minus 0.5987, which is going to be, let's do that. 1 minus 0.5987 gives us 0.4013, which is less than 50%, but definitely greater than 16%. I'm going to show you really quickly a way to do that on your calculator instead of looking it up on your table. So here's how you do it on your calculator. You do second bars. Right there is a normal CDF. The area we want starts, if you'll take a look back here, the area we want starts at 270 and goes up forever. So I'm going to put the lower bound of 270 in. Infinity in this calculator is 1 to the 99th power. So you do 1, and then second comma gives you your scientific notation E, and then put in 99. Our mean was 266, and our standard deviation was 16. And if you hit paste and enter, you can see it's almost identical to what our table gave us. We get 0.4012937, which will in fact round to 0.4013. So if you would like to start using the calculator, you may, but you do not have to. I will work on that when we get back. All right, moving right along. The next part, which I think is the bottom of your worksheet, asks you to take a sample of size 6. So let's go through that real quickly. Okay, so now I want my n to equal 6 and let x be the mean, x bar be the mean pregnancy for the sample. So what is the mean of the sampling distribution of x bar? That is the words for mu sub x bar. And I know that mu sub x bar equals 266 because mu sub x bar is an unbiased estimator of mu due to the simple random sampling and the fact that the mean of the sampling distribution is a very good statistic to use for the mean to infer the mean of the population. Okay, compute the standard deviation, check that the 10% condition is met. The standard deviation of the sampling distribution, those words are the symbol sigma sub x bar. So let's do is 6 less than or equal to 1/10 of all pregnant women. And I think it's safe to say that 60 is less than or equal to all pregnant women. So my sigma sub x bar is going to equal 16 divided by the square root of 6. And if we take a look at that, that happens to be 6.532. And I'll just use 6.53 when we get down to the other. All right, it didn't ask us to check the shape, but I know that the shape of this sampling distribution is approximately normal because the population distribution was approximately normal. So now we're going to do what's the probability that 6 women would exceed 270 days. So it's very, very similar to the last problem, except for my spread is not as big, and that's a little bit deceiving because we're using the same shape. This sampling distribution is actually going to be much skinnier than the last one that we used, but again, because we're doing it with this shape in mind, it's a little bit deceiving. So this is where 266 is. Let me go calculate with norm dist again. I want 6.53. So program norm dist. The mean is 266. Standard deviation is 6.53. So these are the numbers I'm going to use this time. And let me move that over there. So this is going to be 246.41, 252.94, 259.47, 266, 272.53, 279.06, 285.59. So now 270 is a little bit closer to the 1 than it was last time. And that is now equal to an x bar because it does represent the mean of a sample of size 6. So we continue on with the probability that a mean of 6 women, and this is again where n is equaling 6, so we have a different sampling distribution. What's the chance that all 6 women last more than 270 days of pregnancy? Well, that z-score again is going to be a positive 0 point something, and we'll see what that is going to be equal to. Again, I know it's going to be larger than 16, but it's going to be less than 1. Probably much less than the 40% we got before. So how do we find z-score? We take your score, which is 270 minus the mean, 266 divided by 6.53. And that's going to give us 4 divided by 6.53, which is a lot less than 0.25 now. 4 divided by 6.53. Let's see if I can do that. And that gets me 0.6125. 0.613. 0.613. So this is about 0.61. And if I use my table, I get 0.6 and 1 gives me 7291, which is again this way. This is 0.7291. I believe that's what I said. Let me check. Yep, right here. Okay. So my answer is going to be, again, the 1 minus 0.7291, which is approximately 1 minus 0.7291, 27.09%. All right. If you want to check to see if that is what your calculator would give you, I'll do that real quick. Second bars, we have a normal CDF. We're starting at 270 going to infinity now. The mean is still 266, but the standard deviation is 6.53. And when I put that in, it gives me 0.27008, which is very, very close to what we got on the table. So I didn't talk about what the conclusions were. So let me go back to the conclusion for a sample of size 1. That conclusion would basically be there's not convincing evidence against the claim of 266. A sample of size 1 taken from 260, from a mean of 266. Days of carrying a baby, 270 days or more, is 40% of the time by chance. So a lot of women carry their babies longer than the mean. And for this one, it's not quite as likely as that 6 ladies would do it, but it is fairly likely. And we would say something like, well, let's see. So we would say something like the following. Assuming the mean, which is the population mean, or average of carrying a baby, is 266 days. A sample of 6 women carrying their babies (270 or more days) is fairly likely at 0.2709, I'm sorry, 2709, or a 27% chance of that occurring. And we wouldn't be suspectful of that. All right, take a pause, and we have one more instance to look at here. Let me go back to there we go. Okay, so we have done this for populations that are normal. The next thing we're going to take a look at is what happens if the population isn't normal. And when I get back, we'll look at this in more detail, but the central limit theorem, which is part of what you're doing with the pennies, and that will hopefully finish today or tomorrow, tells us if the population is not normal, then the sampling distribution is not going to be normal unless your sample size is big enough to overcome the weird shaped population distribution. So that's called the central limit theorem. And it says that if you take a large enough n, then the sampling distribution of x bar, which is mu sub x bar, its shape, will be normal. So on the next slide, it shows you here that we have a population that is very skewed to the right, and they took a sample of size 100, and now you can see that on this side, it is approximately normal, and it happens to be centered at the same place that the population was centered. We're going to do an app that takes you through this and shows you that the bigger the sample size, the skinnier and skinnier the sampling spread, sample distribution spread gets, and that's called the variability of the sampling distribution. But for right now, just know that if your n is big enough, then you can overcome any unusual shaped population. How big is big enough is a good question, and in most cases, they're going to say that n has to be greater than or equal to 30. So 30 seems the key. Here is a population. You're taking sample x bars. We take those sample x bars and we plot them on this sampling distribution like we did with the class sizes and heights. And all those little x bars fill up this sampling distribution, which has a center where rho is. So even though mu sub x bar is not the same location as mu, they are equal in value. All right. And we still have the center condition and the spread condition, and now the shape condition, instead of it being called large counts, it's the central limit theorem, and again, your n has to be greater than 30. All right, so here is another worksheet and a problem on this. It says David's iPod has 10,000 songs. The distribution of the playing times for these songs is heavily skewed to the right with a mean of 255 seconds, standard deviation of 60 seconds. Suppose we choose a simple random sample of 10 songs from the population. Calculate the mean and play time of the songs. What are the mean and the standard deviation of the sampling distribution? Explain. So see if you can do that. You can pause the video. The answers are on the next slide. Okay. This is the answers on the next slide. Please, very importantly, notice that even though it's heavily left or right skewed, we can still find the center and we can still find the spread. We just don't know what the shape of the standard deviation will be like because 10 is not big enough. So the mean of the sampling distribution is going to be 225 seconds. It's true because a simple random sample was used, and the mean of the sampling distribution, which is mu sub x bar, is an unbiased estimator of the population mean, which is mu. And then standard deviation of the sampling distribution, I don't think we're overachieving. 10% would be 100, and it's told us that he has 10,000 songs. And so 100 is definitely less than the 10,000, and so I can apply the formula which is sigma sub x bar, is the sigma of the population, which is 60 seconds, divided by the square root of 10, and we get 18.974 seconds. All right, the next one, it says, how many songs would you need to sample if you wanted the standard deviation to be 30 seconds? Instead of, back here, we saw that it was 60 seconds. So if we want to cut the standard deviation in half, down to 30, I think most of you guys already probably know the answer to this, but in case you don't know the answer, there is a way to work it out. So I'll show you through these slides. We want 60 divided by the square root of something to equal 30. So mathematically, if I multiplied both sides by the square root of n to remove the square root of n from the denominator, I would then have 60 equals 30 times the square root of n. Dividing both sides by 30, I end up with 2 equals the square root of n. And when I square that, I get a sample size of 4. So if I wanted to take that standard deviation from 60 to 30, I would need a standard deviation, a sample size of 4. And I think some of you knew that it would have to be 4 times bigger, and 4 times bigger than the 1 is 4. Explain why you can't safely calculate the probability that the mean playing time is more than 4 minutes for a simple random sample of 10 songs. Well, since the population is severely skewed, we have to have a sample size that is bigger than 30, and 10 is definitely not bigger than 30, so that doesn't work. So finally, the last problem. Suppose we take a simple random sample of 36 songs instead. Explain how the central limit theorem allows us to find the probability that the mean played time is more than 240 seconds. Calculate this probability, show your work. On this first slide, I'm going to take you through the 3 checks. So let's do the center check. What is mu sub x bar? Well, mu sub x bar is 200, is not 200. If we go back to the first one, mu sub x bar is 225, standard deviation of 60. All right, so let me write down our givens. We have 225, which is mu. Our sigma is, I don't remember. All right, our sigma is 60. Our capital N is 10,000. So this is 60 seconds. This is seconds. And our capital N is 10,000. Right now, our small case n, our sample size is 36, and I believe they said that it's severely right skewed is the population. Let me double check. Yep, heavily skewed to the right. Okay, so let's check the center. I know that mu sub x bar equals 225 because mu sub x bar is an unbiased estimator of mu due to my simple random sampling. All right, the next check I have to do is the spread. And this is called the 10% condition. So let's take our n, which is 36. Is 36 less than or equal to 1/10 capital N, which was 10,000, if you'll remember. And 360 does seem to be less than or equal to 10,000. So I know that I can find my new sigma sub x bar by taking 60 divided by the square root of 36, which is 60 divided by 6, which is 10 seconds. And then finally, my shape. The shape distribution. Well, I know that my population distribution was heavily right skewed. So there's no large counts. There's no n and p thing to do. Right now, I have to check what n is, and it was 36. And so the central limit theorem tells me it says that if my sample size is greater than or equal to 30 and 36 is greater than or equal to 30, then the sampling distribution of X bar is approximately normally distributed. So back in the other world of rho p hat, we were using the normal distribution to approximate a binomial distribution. Here, our distributions can be really whacked out and crazy, maybe skewed, maybe not. But the central limit theorem covers us because we're doing 36. So now I would like you to finish the rest of the problem by filling out everything on the sampling distribution. You want to know what the probability of an X bar, remembering that n is equal to 36, the probability that an X bar is more than 240 seconds. So you have to change that into a Z and look everything up. The answers are on the next page, so go ahead and have the substitute pause the recording. Okay, so here we are. I hope you have your N up here because that helps you remember what's supposed to go in the middle. Big confusion comes with people trying to figure out if you're using the 225 or the 240 in the middle. This will help you. I put my norm dist on. I have my Z scale, my X scale, 240. Need to write that down. That equals an X bar. I'm clearly shading greater than. To find Z score, I take 240, which is your score, minus the mean of 225 divided by 10. I get a 1.5. When I looked it up on the table, I'd have to do 1 minus to get this answer. But I will show you real quickly again how to do that on your calculator, and that is second distribution, normal CDF. I'm going from 240 to infinity with a mean of 225 and a standard deviation of 10. And that gets me 0.668. And that is pretty much identical to what we got on the table. And you don't have to put a conclusion here, but that's somehow this person got a little bit unlucky and randomly picked 36 songs that were kind of on the long side. So it can happen, certainly by chance. It happens 6% of the time, 6.6, almost 7. But this is getting a little bit questionable. Okay, finally, that is the end of the first video, except for let me tell you that your homework, and this is Chapter 7, number 5, I believe, not number 4. Pretty confident this is, it's either 5 or 6. I have to go back and look at the beginning. So I'll do that for you real quick. It is number 5. So number 5, assignment. And the A-skip is 54. Show all your work, reasons, notations, z-scores, calculations, curves, etc., etc. You can look online for some help because, as you can see here, I have some of the things crossed out, but definitely go on to the slides to look for some help. And we have, if there's time, one more little video to help you start doing some of the rest of the central limit theorem with the coins. All right, thanks for your attention.